Good afternoon, colleagues. Thank you, Program Director, for the nice introduction. Okay, so I'll be talking about the work that we've been doing, hosted by the CHPC. We've been working together for the past almost 10 years now, isn't it? We are the earliest guinea pigs for the OpenStack. Yeah, yeah, thanks. So this work is about this product or a system that we've developed, which enables network operators, wireless network operators, to access radio access frequency spectrum to provide affordable broadband connectivity. And our aim is actually to reduce the cost to communicate in rural, hard to reach, and underserved areas. My slides are not moving. They're not moving. It's moving.
Just close it. Let's reopen it. Which one's yours? This one. That one. Yeah, it's fine. Sorry about the technology, So, yeah, sorry about that.
I'll be using these things. Okay, looking good. So this is the outline. So I'll give you a bit of context about the work and rationale. Then we'll talk about the affordability dilemma. I'm talking about broadband connectivity affordability. And I'll give an overview of relative costs to provide broadband access, especially in rural, remote areas. The concept of dynamic spectrum access and how we tackle the aspect of affordability. Then I'll provide the highlights as the program director mentioned, and the conclusion and some ongoing work that we're currently doing. So we are all aware that broadband access is very crucial to achieving the so-called Sustainable Development Goals, which they are in line with the National Development Plan for any nation, especially at this age of the fourth industrial revolution, because most of the applications that we are talking about, for IR applications, they actually need connectivity, and the connectivity should be affordable to every citizen. If you look at the picture there, it is from the United Nations, highlighting the 17 SDGs. You can see almost 50% or above 50%, they actually require connectivity from you. Learning from home, working from home, and so forth. But sadly, stats are not in our favor, especially for us from the southern Saharan part of the continent, where only 33% connected to broadband connectivity. And worse, according to the UNESCO, which is one of the UN agency, a survey taken to about 10 countries in Latin America, Africa, and Asia, 30 to 50% of women are likely to actually to be connected to the internet. Globally, it's around 23% of women who are less likely to be connected. And the biggest challenge is actually affordability. So you'll find some people who are living within coverage, but they can't meaningfully uh, connect to broadband. And this might even lead to another divide, which is called the digital industrial revolution divide, because you need connectivity to participate in the 4IR, 5IR, and all the industrial revolutions. So talking about the affordability, the dilemma. Here, I'm trying to bring into context the cost to communicate, especially in South Africa, vis-a-vis other essential needs. For example, putting food on the table. You can see that almost 23% of South African households, they are struggling to put food on the table. The average food basket in the country is around 270, I think, rand, if you convert that. While the average cost of 1 gigabyte, if you've noticed, is around 1.18 US dollars. If you convert, I don't know what is the rate today. This will translate to around 10% of your money that you want to put food on the table. So then the question will be, if you are living in a rural area, should I buy data or should I buy bread for kids, right? So if you look from the telecommunication industry perspective, some of the costs which cause all of these issues of unaffordability are mainly caused by infrastructure itself, the equipment, and radio frequency spectrum. I don't know if you are aware of the auctions which are normally carried out by the regulator ICASA. When you go to the auctions, you'll find that the cost of spectrum is so high. I think 3 years ago, when they did the last auction, 4 operators, the big ones, I don't want to mention their names, they raised around close to 15 billion rand just to buy a small piece of spectrum. And spectrum is very important to wireless communication, because you need the spectrum to communicate. There are no wires. So now what will happen is that the operators will now have to make you pay, because they've bought the spectrum, then you have to pay to recoup their investment. And if you look at the map there, I'm trying to bring into context the percentage of connectivity by province. Here I'm talking about fixed connectivity at home. I'm not talking about mobile. If you look, in most provinces, the percentage is very low. Nationally, the percentage of connectivity at home, people who have internet at home, not through the mobile phone, it's less than 30%. So the question is, how do we reduce the cost to communicate, or how do we support operators to reduce the cost to communicate while providing quality connectivity? So the picture on the left-hand side actually shows the cost relative to the area. Of course, we understand that fiber is one of the best form of communication if you have it. But unfortunately, fiber is more relevant within the urban areas. It's easier to connect someone in urban areas than when someone is going outside the CBDs and in rural areas. So the graph there shows you how the cost increased by technology. You can see fiber, satellite, and so forth. You'll see some other technologies, wireless-based, like TV Wi-Space, which I will talk about. But the aim here is to maximize the value of communication, which is the quality of service, while reducing the cost. So here now I'll start talking about the work that we've been doing around dynamic spectrum access, which is a technique in telecommunication which allows one to access radio frequency spectrum opportunistically. And this will actually allow now operators to have spectrum without paying so much fees, and also allow the regulator, like ICASA, to actually efficiently utilize spectrum. So how does it work? With DSA techniques allows one to share spectrum, which is already being used by, or in use by other operators, or allocated at a given time, space, and it can be in other dimensions. Case in example, in the bands which is allocated to broadcasting, where you see SABC, ETV, one can use the very same spectrum used by SABC in a location to provide other services, in this case, let's say broadband connectivity, without causing interference to the broadcaster. So this is the work that we've been doing for almost the past 7-8 years on how we can exploit that spectrum within 470 to 698 used by broadcasters to provide the connectivity in rural areas without going to the auctions. And the reason being why we chose that part, this is so-called UHF, ultra high frequency, frequency. That's the area where the signals, properties of the band allows signal to travel very, very long ranges and even penetrating man-made and natural obstacles. And this is the reason why people in rural areas, they can even watch TV using those small antennas, if you remember back in the days during the analog time. So this area of band can actually allows us now to provide broadband in rural areas effectively with low cost without causing interference to broadcasters. So how do you tackle that? The work that we've developed now to achieve that is we've developed something called geolocation spectrum database. This is a system which performs calculations to find where are those spectrum holes, areas where broadcasters are, but are not active at a given time and space. Then we reallocate that spectrum to radio equipment, which now will provide broadband connectivity. In a nutshell, we get the spectrum, we harness it from the area of interest, then allocate it to operators dynamically. So just to give you a bit overview on how this is done. So the picture there shows those towers. If you go outside, you'll see on the mountains some towers. Some of them, they are operated by mobile operators, some of them by broadcasters. So in this case, the broadcasters ones are the ones that we are trying to see where the broadcaster is active at a given time. Then we do our modeling, and then we can find the gaps, the spectrum, the so-called TV white space. So our models actually shows, for example, in any given area within the country, up to 60% of the land, you can find up to 25 empty or channels that are not active, which now one can utilize them to provide broadband. That heat map down there is a model that we did for Tshwane municipality, which shows, you can see the color coding there. In most areas, you find a lot of channels, up to 28 channels that are not being used. But if you use our technique, then operators can provide broadband. So this is where DORA comes in. So this is an overview of the high-level architecture of the system that we've developed. Since this kind of work also involves regulatory aspects, so we developed 2 systems. One sits with a regulator, Independent Communication Authority of South Africa, ICASA, which is called the Reference Geolocation Spectrum Database. And I'm glad some of the colleagues who supported development of this work, Muzi and Doctor there, you remember when we were doing this work back in the days. Yeah, so the reference part sits with the ICASA, the authority, and the other part is called the secondary database, which is operated by any accredited entity through the authority, ICASA. But when we develop this, everything actually is hosted at CHPC, but the management of these parts are differentiated. The other part is managed by ICASA, the other part is managed by the parties which have been accredited by ICASA. So it is a system which has a calculation engine. A calculation engine is the place where now our algorithm runs. We do all the radio propagations using terrain data set from the authority with all the transmitters. Yeah, so we perform that and allocate to devices, network devices. So this system is already hosted. You can access through that URL down there. It is web-based, but for devices like base stations used by network operators, they connect to the system via the APIs. So the network device, like a base station, will query periodically to see what is available without human intervention. And the system will say you have 10 megahertz at this location, at that location. So there are some rules and regulations built around the algorithm and the system on how to access. And this is what had been happening. Network operators using the platform. So we think this system will actually reduce the cost to communicate, because without now going through those competitive licensing auctions and pay billions, one can access this spectrum using the system. So some of the use cases, of course, the main use case for us is to reduce the cost to communicate in rural areas. So rural broadband connectivity is at the core, but other emerging use cases like private and enterprise networks comes to mind. You can deploy that. Security, CCTV camera, and Internet of Things. All that is possible using this spectrum. So talking about the impact, so we didn't just end developing the platform. We also, in collaboration with development partners like UNDP and the British government, empowered women and youth-owned SMMEs. We trained them, capacitated them, provide them with equipment, and turned them into network operators in their communities. So we have supported a number of them. As you can see in the map, we have a number, I think 3 here in Eastern Cape, KZN, there are 3. In total, we have supported over the past 3 years around 13 these network operators who are using the platform to provide affordable broadband connectivity in their areas. And you can see the pictures, some of the schools connected, so the towers. So it's a full functioning, small, low-cost telecommunication platform that one can use to provide broadband. If you want to see the numbers, how many job opportunities that have been created, number of people and household connected, you can see it by yourself from that picture there. So we didn't end locally. We also, we've been taking our innovation and collaboration internationally. Through CHPC, again, we have created instances to other partnering institutions. For example, European University of Cyprus. We supported them with an instance hosted at CHPC, University of Dodoma and University of Dar es Salaam in Tanzania. Also Botswana, I think that is Botswana Innovation Technology Agency or something like that. Through our MOUs and research collaboration. But in 2016, we were also certified to provide this service in the UK market. All right, so in conclusion, I'm coming to the end. This work actually supported a number of local communities, SMMEs, to achieve or towards advancements of the Sustainable Development Goals, SDG 1, 2, 3, 6, I think, 9. And as I mentioned, some of the use cases, one can use the platform to provide a rural broadband connectivity, private enterprise networks, security, and Internet of Things. And we really appreciate and welcome collaboration to take this product to the communities. So currently, we have moved now the area of research to the higher band. This is 3.8 gigahertz to 4.2. This is an area which currently is being used by satellite operators, fixed satellite operators and fixed services. And the work we are doing now is to almost replicate the work we are doing in the band which is used by broadcasters to also make that spectrum available to new entrants and small players who will be providing affordable broadband connectivity. Thank you so much.